Hey there, we are going to start talking about sequences and specifically in this section, mathematical patterns. So I'm turning back to what is chapter 9 in my book. And we'll begin with the word sequence. That is an ordered list of numbers. That's what this section is going to be all about. We'll keep it pretty short. This section is only going to be a few days. Then next, the term of a sequence. That is any individual number in a sequence. So for example, we could have a very common sequence, which is our counting numbers. So we would start with 1, go to 2, go to 3. That would go on as far as we would want. And we could start using variables. We could say we have the number n. The number before that would be n minus 1. We just take 1 away from it. The number after that would be n plus 1. We would add 1 to it. So we refer to the first term in any sequence as a sub 1. The second term in a sequence is a sub 2. Third term is a sub 3. The nth term, whatever that number n is a sub n. The one before it is a sub n minus 1. The one after it is a sub n plus 1. I'm not going to try to drill too much of that terminology and writing style into you. Just wanted you all to see that first. And then a big thing we're going to talk about is the explicit formula, which is a description of the nth term of a sequence using the number n. So this may make more sense after this example. Example 1, generate the first 5 terms of the sequence defined by a sub n equals 3n minus 2. So if we want to find the first term of a sequence, that is a sub 1. So if we want to find the first term, a sub 1, we are going to replace the n with a 1 in the problem. So that's going to be 3 times 1 minus 2. So that's 3 minus 2. I'll go ahead and get all the way through there, which is 1. So the first term in this sequence is going to be the number 1. Then the second term would be a sub 2. So we would replace n with a 2. So it's 3 times 2 minus 2, which is 6 minus 2, or 4. The third term would be 3 times 3 minus 2, which is 9 minus 2, or 7. The fourth term would be 3 times 4 minus 2, which is 12 minus 2, or 10. And at this point, you may just recognize the pattern in this sequence of numbers. We're starting with the number 1, and we are adding 3 each time. So the next term in this sequence would be 13. So you might be able to just kind of skip ahead once you securely identify the pattern. But that's how we would use the explicit formula. So this could be helpful if I wanted to find the 100th term of this sequence. I would just put the number 100 substituted for n and simplify that, and we would get the 100th term, which without actually having to count all the way up to the 100th term and getting everything in between. A little bit more on this one. So the recursive formula, that is a different type. That's not the explicit formula, it's the recursive, and it tells you how to go from one term to the next. So the recursive formula for example 1, in that example, we can see that we are adding 3 each time. So I'm just going to have us do this. I'm just going to say add 3. That's a little more basic than what the textbook does and maybe what a lot of people would be used to, but there is a more complicated formula. For now, I'm just going to say that we can describe the recursive formula, and to go from one term to the next, all we have to do is add 3 to the previous term. So then here for example 2, write a recursive formula for the sequence, then find the 10th term in the sequence. So here we've got a few different ways that we can order a sequence. A very common one is to add or subtract something. So if we want to figure out how we go from one term to the next, if this is addition, to go from 4 to 11, I can reverse that and do 11 minus 4. There's 7 in between those. So if we do 4 plus 7, that would give me 11. But if I add 7 again, that does not give me 32. It gives me 18. So adding 7 is not the pattern. Another thing that we could do is potentially multiplication. That would get us bigger to go from 4 to 11. So if we went to undo that and figure out what that is, that'd be 11 divided by 4, which is 2.75. So 4 times 2.75 gives me 11. 11 times 2.75 gives me 30.25. So we're not too far off in this case, but that's still not correct. So there are a few other ways that we could do this theoretically. I'm not going to make these all too complicated. You may look at this and realize that multiplying by 2.75 might have been close. It wasn't quite it. But from one number to the next is not an exact multiple, but each of these is really close to being 3 off. So when you divide 11 by 4, you get 2.75. When you divide 32 by 11, you get 2.909 with the 09 repeating, or the 90 repeating. And then if you divide 95 by 32, we get 2.96875. So these are all really close to 3. So see what happens if we multiply 4 by 3, that gets me 12. If I multiply 11 by 3, that gives me 33. If I multiply 32 by 3, that gives me 96. So those are all exactly 1 away. The recursive formula here, we could say, is just multiply by 3, then subtract 1. So if we take the number 4 and we multiply it by 3 and then subtract 1, that gives me 11. If I do that again, I get 32. If I get that again, I get 95. So then if we continue this, 4, 11, 32, 95. If I do that once more, I get 284. Then 851. So we got 1, 2, 3, 4, 5, 6. The 7th term is 2,552. The 8th is 7,655. The 9th is 22,964. And then the 10th term, 1, 2, 3, 4, 5, 6, 7, 8, 9. The 10th term is 68,891.